Hello everyone. Uh, Welcome to the next topic called electrochemistry, electromagnetic spectrum. Okay. Now, when it comes to electromagnetic spectrum, first thing you should understand is what we call it as the wave characteristics. Okay. And what exactly is this wave characteristic? That given any wave, how does that behave, and what are its parameters? So any wave propagates in one direction. So for instance, this wave is propagating in this direction. Now, what exactly this mean that from here, because of certain vibrations on the mean position, something like this, okay, any particle which vibrates in its mean position this way will definitely give its effect in the form of wave. That effect may be some sound energy or more like ripples in water or light which travels. So all those energies will always be traveling in the form of wave. And what are the different parameters we use in the wave is to define the peaks here are known as crests, and the depths which are being made, these are called troughs. Okay. So this is also the second crest and this is trough. The amount of length that has been swept in y-axis, this is called amplitude, and the distance between two crests, this one between two crests, is defined as lambda, or also known as wavelength, and which is our first characteristic. So wavelength is lambda. Okay. So I can write that as distance between two successive crests or troughs. And we usually denote wavelength in centimeters or meters. And next important characteristic is what we call it as frequency. We denote frequency as nu. Okay. This symbol is called nu, nu, nu. And what exactly is frequency? Frequency is the amount of waves or the number of waves that has been traveled at a particular place per second. So consider if I am standing here and trying to visualize how many number of waves it can travel from this point per second, that denotes my frequency. So for instance, this entire thing from this point on to this point, this is one wave, and from this point on to this wave, this is my second wave. Okay. So how much time, or how many number of waves that can be travel from at this position per second defines my frequency. So therefore, frequency is nothing but number of waves crossing in unit time. Okay. So this is the second important feature. Next we have speed or velocity of a wave. What is this? This is the amount of speed with which the wave is traveling. So for instance, if I say c is the speed, then c will be equal to distance covered by the wave by time taken. How much distance it is traveling, it is covering. Let us say if it travels alpha distance and time taken for one wave is t. So therefore lambda into 1 by t is what we can define it as speed c, but we just know that lambda is the wavelength and 1 by t, 1 by time is nothing but frequency. That means this is the number, this is the amount of time taken for particular number of waves to cross at a particular point. So I can write that as nu. So it implies c is equal to nu lambda. Okay, this is a very important conversion. So c is equal to nu lambda is a very important formula we will be using. So just to remind you once again, we discuss what are the different wave characteristics, and main importantly three wave characteristics. Every wave will have crests and troughs. Distance between two crests or two troughs is what we call it as wavelength. Then number of waves crossing in unit time, we call that as frequency, and we denote frequency as nothing but 1 by time. So I'll write it here. Frequency nu will be equal to 1 by time. And we also discuss another wave characteristic, which is speed or velocity of wave, which is nothing but the amount of distance traveled by time taken. So distance traveled is lambda and time taken is t. So lambda into 1 by t is what we call it as distance, which is c is equal to nu lambda or lambda nu. Okay. We just saw that uh, velocity of any wave can be given as c, and usually this letter c is used majorly for speed of light. Okay. So if we consider that light is traveling as wave, then its speed would be equal to uh, nu or lambda nu. Okay. So and this has been found that it is always constant in vacuum, and which is equal to 3 into 10 raised to power 8 meters per second. So that means this is the amount of speed with which light travels. Okay. And this has been found constant. That means for any particular wave or lambda, the speed of light is always constant. इसका मतलब क्या है कि if lambda is increasing, then nu would decrease, so that the product of these two would always reach this. Okay. Similarly, if lambda is decreasing, then nu value will increase such that the product of those two will always remain this number. Okay. So this is the constant number which is found for speed of light. The fourth important parameter which we will see is what we call it as wave number. Okay. So wave number is denoted as nu bar. Okay. So there is a bar here, line here. So what is wave number? So wave number is the number of waves. Okay. Number of waves per unit distance. So if at all I take any wavelength, so let's just to give you a brief idea. So if this is how the number of waves are traveling, then consider if this entire thing is 1 centimeter. Okay. In this 1 centimeter, how many number of waves you can have it? Like for instance, you can see this is one wave, second wave, right? So that means in 1 centimeter distance there are two waves present. So therefore my wave number will be 2. Okay, so I write this also as wave number is equal to 1 by lambda, which can be represented in centimeter inverse or meter inverse. Okay, that means wave number is nothing but the number of waves traveling per unit distance. Okay, so if I take my unit as 1 centimeter, you can see there are two waves. Okay, so there might be 100 waves, 200 waves, so that gives your wave number. Yeah, so therefore in electromagnetic spectrum you would usually come across these four important terms. Okay, one was, just to brief you, one was wavelength. Next we learned frequency, then we learned what is speed of light or velocity of a wave, then finally wave number. Okay, these are the important things which you might be coming across. See, when it comes to electromagnetic spectrum, just to give you a brief idea what exactly this electromagnetic spectrum is all about and how does it look. Now we see a lot of things around us, everything so colorful. Okay, uh, things which we call it as radio, refrigerator, then we have remote, cell phones, we have television. There is one thing in common in all of them, that it is all driving everything which we are seeing, feeling is because of electromagnetic radiation. These are gamma rays, X rays, ultraviolet rays, visible rays, infrared rays, microwaves, radio waves. All of these radiations are being emitted from the source of sun. Okay. Now if you see it, for instance, this wavelength is very long, right? Okay, you can see they are quite big. So all these bigger wavelength we have categorized this entire section as radio waves, which is what we usually use in radios. Then we have another section, this entire section, which is what we call it as infrared waves, right? Which we usually use in remotes. Okay? And we also use some section of microwaves and some section of radio waves for using that in cell phones. Okay, and this portion is usually used, this entire thing, which is called as visible region, because we could see those colors, right? So this is a visible region, which is what our TV reflects us. Okay. Then we have microwaves here, which is usually used in our micro ovens. Then we have refrigerators in which there are again some microwaves been running. Okay. Now usually what is the difference between a simple water wave and our usual electromagnetic wave? In water waves, you see it is unidirection. Okay, a wave is created and it propagates in one particular direction. While when it comes to electromagnetic radiation, now you could see there are two types of waves. Okay, one always, both of them propagates in the same direction, but both of these waves are orthogonal to each other. That means perpendicularly aligned. Okay, so you can see if electrical wave is traveling in this way, then the magnetic wave will definitely travel in this way, and both of them perpendicular to each other. This is how the electromagnetic radiation propagates. As we discussed, the peaks are called crest and depths are called troughs, and the distance between two crests or troughs is called wavelength. We usually measure that in meters or centimeters. Nanometers, it's the smallest unit, which is 10 power 9 times, okay, to 1 meter. And then we see this is frequency, number of waves traveling per second. This is what we discussed. How many number of 3 hertz? Hertz means per second. So if at all you see in terms of energy, this is a radio wave which has a very long wavelength and short, okay, very less amount of frequency. So therefore the energy will be very less. It has been identified that energy of a particular wave depends upon its wavelength or frequency. If the frequency is very less, energy will be less, and wavelength is very large, energy will be less. So as you go ahead, you see how the energy is increasing, okay, how the frequency is also increasing. As you come over to gamma rays, huge amount of frequency, so that's why energy is higher. We usually see there are a lot of radiations coming out of television, which is what we usually see. Apart of it, if you realize that there are so many different radiations also present in our room, okay? So there are a lot of different radiations coming inside. Some radio waves, maybe microwaves, ultraviolet rays, infrared rays. But are we able to see all these radiations? Not exactly. We can only see certain amount of radiations out of it. I think you might realize that we are only able to see this visible part. Okay, we cannot see all other radiations, but just this visible part. Okay, so if at all I remove all those radiations and I only keep visible part, which is what coming from the television. Okay, now we don't see anything which is completely plain white around. We always see colors around us, right? So how exactly these colors coming? You see, lot of these things which are supposed to be just white, okay? Because when I say visible reason, if you mix all the colors we know, it turns out to be white. So then why can't we see everything as white? Rather we see so distinct colors for everything else. So where exactly these colors are coming from? Let us imagine a simple leaf. Okay? So in this leaf, it always appears to be green in color. What probably might be the reason is when the radiation is falling on that leaf, only the green light is being reflected. Rest of all the radiations is being absorbed. So the reflected light is what we see. Okay. So see, this is what is happening. A white light falls on the leaf. Everything, all the colors get absorbed inside except the green part. So green part is the one which is reflected. So this is the same thing happens around us. And now what are these radiations? As it absorbs, within no time, the energy is again emitted back. And this time the energy may come as maybe gamma rays, maybe ultraviolet rays, maybe infrared rays. So it depends upon the nature of that leaf or the atoms present in that leaf, that what exactly it should propagate. Should it give ultraviolet? Should it give gamma rays or anything? Okay. But one thing you will see sharp color is green is because it is reflected. It is a reflected color, and rest absorbed energy from this white light is again converted back into something new. It could be a gamma ray, ultraviolet ray, or anything else. So we see around a lot of things, X-rays, then we see around uh, climate changes. All of these are been observed in different types of photographs. Okay, those could be ultraviolet photographs, those could be infrared photographs, microwaves. Okay, and that is how we predict even the seasons. Yeah, and when it comes to electromagnetic radiation, you see a white light when it passes through a prism, okay, it start refracting and start showing all the colors. This is how the white light enters into the prism, get refracted and shows all these colors. Okay, and we call this as Vibgyor, as it starts from violet and ends with red. And the wavelength of violet is around 4000 Armstrongs. Okay, this is the unit we usually use. Okay, and what exactly is Armstrongs? One Armstrong, 1 Armstrong is equivalent to 10 power minus 10 meters. Similarly, 1 nanometer is equivalent to 10 raised to power minus 9 meters. 1 picometer is equal to 10 raised to power minus 12 meters. I would want everybody to remember these three conversions, because while problem solving, this becomes a very important term. Okay, what are Armstrongs, what is nanometer, and what is picometer? Clear? So 4000 Armstrongs, as in 4000 into 10 raised to power minus 10 meters, that would be the wavelength of violet color. Similarly, we have 6500 for red color. This is how we have a complete what do you say, colors forming from violet towards red. And since all the color merge in the other, like you can see violet slowly getting, from here you can see the violet is slowly getting converted into something new color. Okay, again that's getting slowly mixed into another color. So these are called a continuous spectrum, because they will not have any distinction somewhere in between. It is completely fading a color and then generating a new color. So therefore these are called continuous spectrum. Clear? Let's try to do a simple problem. Uh, Imagine if at all I gave you wavelength of an electromagnetic spectrum. Okay, and I need to find out what is the frequency and wave number of a spectrum. Okay, so how do we solve this? These are the usual questions you will come across कि आपको शायद wavelength दिया जाएगा, frequency और wave number find करना हो, या sometimes you will be given frequency और आपको शायद wave length calculate करना हो. In either of the case, we know that C is equal to nu lambda. ये सबसे important formula है जो आपको याद करना है. And we know the value of C, which is always constant, 3 into 10 raised to power 8 meters per second. So अभी कैसे solve करें? Lambda is given as 6500 Armstrongs, and frequency will be equal to C by lambda. I can write this. So frequency nu will be equal to C. C is given as 3 into 10 raised to power 8 divided by 6500. But ये 6500 किस में है? Armstrongs में. So convert that into meters, right? Because 1 Armstrong is equal to 10 power minus 10 meters. So this is given in meters per second already, और ये बन जाएगा now in meters. Sorry, now this entire thing will become in meters. Okay, so if at all we calculate that, how much it will be? Let us see. 3 we have to divide it by 65. So 3 divided by 65 comes to be around 0.046 multiplied by 10 raised to power 8 into 10 raised to power. Can you see here there were two zeros here, so if at all I cancel with this, that would become 10 power minus 8. So that 10 power minus 8, if I bring it to the numerator, it will become 10 power 8. So therefore this will be 0.046 into 10 raised to power 16 per second, right? Because this will be the units in per second. This was meters per second. Meter gets cancelled, you see. These are the units that get cancelled, and you will be left out with only second. So which is equal to, can I write this as 4.6 into 10 raised to power 14 per second. So what does that mean? These are the number of waves that can travel per second. Okay. So 6500 Armstrongs, if you remember, this was the, oops, sorry. So this was the frequency, 6500 was the wavelength, sorry, of red light. Okay, So a red light will have how many number of waves per second? These are the number of waves a red light can have. Okay, these are the number of waves traveling per second.